Ça, c'est ce qu'on voit sur Zoom, donc c'est bon.
Ouais.
Ça va.
Ouais.
Il y a eu un problème avec le donc on va ça. Hide vidéo panel.
Okay. Yes, thanks to everybody.
The setup is okay, so she's the chair.
Yeah. All right. Yeah. So the next speaker is Guillaume Laibe, talking about Shamrock again. So
yeah. Sorry for the overload. But okay. So thank you everybody. So I call this the Shamrock moment because we are putting a lot of effort to develop Shamrock, and I would like to give you a small perspective on where we are up to, a bit of directions, and to give you some perspectives of where the code is aiming to go in a quick, more or less, future. So just it's a personal tale. So I'm this in-between age. So my first conferences were in 2005. And by that time, it was a big discussion between SPH and grid-based and a lot of physical processes. It came out from this, so the grid-based community was very interesting in the MRI process. It came out from this analysis of the MRI, and it was at the time it was a bit the rush over the resolution to see what is alpha. And so increasing the resolution, so getting more power. And then MPI arrived. Power, and a lot of people were very enthusiastic in keeping the simulation. So it was like a big accretion of the community onto studying this theme. And for example, you see I quoted a paper from Héloïse Méo, Sébastien Froment, 1000 cube MRI simulation with Ramses. So it was a lot of attention. And then in this game, I came out. And where we are doing like simulation with dust and SPH, and it was 100 or 200,000 particles. And I think it was a hard time to convince the community that it was interesting. Really. And we nearly died in a sense, but thanks to Daniel. At least in this community, I think it was and a combination of other factors. I think it was nice re-rise of SPH. Why? Because I think two reasons. First, code issue. So three reasons. First, you have the code, so you can compete with other methods. If you cannot compete with other methods, on my experience, you are doomed. Then you need the physics. And MHD was every conference, yes, but your code cannot do SPH cannot do MHD. And when you say, yeah, it can, yeah, okay, you can discuss. And last, I think it was sufficient. Like even if you cannot reach like the simulation at the time that Sébastien Froment and all these other guys were able to do, the community just changed perspective because of observations. And the resolution you could get with Phantom was sufficient to address like ALMA and shear problems. So I think it's very important. And it gives you also like some historical perspective and some biases of how you end up with having SPH and stuff, at least in this community. Well, there were also plenty of other guys doing this stuff, but it's my own perspective. It's how I see this. And the lesson, so I took a couple of lessons from this. So I talk about Ramses code, so which we are using a lot in Lyon as well, the Phantom code. So a few lessons learned on why these developments were successful. So on one hand, so we had the grid-based, and so Ramses, so it was anticipated development. So the guy were coding Ramses 5 years before, like you had MRI, okay, MPI, and it's just you had very early scaling. So right at the beginning of the code, it was scaling. Okay, so it was very important. And then very early, you had key physics, gravity, radiation aerodynamics, MHD, like Patrick and Bell, Frédéric Bourneau, those guys. They implemented this physics, and it allowed to study a lot of important systems. Can do all scales from cosmology to planets, and also the code like it allows implementation from users. Just user can just implement the thing, and they were allowed to do it. Okay, cool. And then Phantom, more from my side, robustness, I think is very important. So like, I think like people trust the code in the way that, or trust that it's as most trustable as it can be because of a lot of tests, paper. There are key physics to address the kind of problem you want. So I was interested in the dust, so it was dust physics, but you have also other physics that we saw this morning. Key thing is the link with observations. Without MC first, I think it could have not been the same success at some point because you have to compare with observations. Software design was key, so nice way to do setup, documentation, and then strong visualization too. So I think those, so yeah, those, if you have in mind the development of a code, you have to have this in mind, plus the fact that you have an instrumental context. Where is the community going? Theory, instruments, okay. And the way I'm telling you this, because like yesterday we had GPUs. So GPUs is what is this, is the parallel of this, is that when you have the CPU, okay, you have a disordered way of organizing your computation. It's fairly work up to a given stage. But when you have the GPU, if you do some work, a lot of work to organize your calculation, then you are effective. And you are effective as roughly a ratio of the bandwidth between the memory access you can get, and you get for sample power or reduced cost of a factor 10. So okay, so people were interested in going to this direction, and grid-based guys, they realized this early. For example, here in Grenoble, you have the IDFX code, like led by Geoffroy, where you have, and in 2000, like 2 years ago, you already had simulation, a very high resolution simulation of disks, and of course you have other codes. So we in Lyon, we belong to a consortia, Euro HPC, where you have 7 codes that are going to be and very advanced to be ported on GPU for the grid base. So, okay, either you stop doing SPH or you react, and this is a bit what motivates the implementation of Shamrock. What I see also is that a lot now of grants and jobs, they very target like very high resolution. And so for young people, keep this in mind. I could have seen this in the ERC, for example. Okay. So yesterday was GPU, and now today is exascale. So this is the Aurora supercomputer. So Timothy will speak about this guy. I think more impressive is to see the cooling system. So then you can imagine the power you have in this. So it's a quintillion of operation per second on the gigawatt center. So we started to use this cluster. Timothy explained this. A few lessons again, just fresh. So when you are going to these guys, you have to speak with HPC engineers. So you have to absolutely stick to standard, to have templated programming, to deploy your code easily. It's otherwise they don't care. They just let you fix the stuff, and then when it's ready, you go. And then you need for your code to be compatible with the hardware and the supercluster. If you don't have the good hardware, then okay, just don't go. So this is very important. And as Timothy, so far we are able to run 500 billion of SPH particles on the super simple test, not physical, but it gives you an idea of the performance we can achieve. Okay. So why do you want to do this? But it's not obvious. Like why is? Well, I've identified four kind of simulation where what you can do with exascale. First, you can reach for resolution. Resolution, for example, you can resolve the radius of a planet in a disk simulation. Okay, so you can really target. So then you have to, if you think at this, you have to address the CFL condition. You have you have a lot of problems to address. Which is the time set that is dominating your simulation? But this is the first thing you can do. Second stuff, you can go for integration. So we can let and integrate longer. Okay, because it's faster. So for example, even if you have a moderate size simulation, but you can form a star and then after hope for the formation of a planet. It's possible. Your statistics. So for example, with one Aurora simulation, in potential, you can generate in one simulation all the disks that have been generated by Ramses so far. So statistics is important. Okay, and it's there is a trade-off because you cannot do. It's possible not to do one exascale simulation, but just a pre-exascale with a lot of statistics. Okay, and then you can do also environment. So this is the cheapest way to think the thing because you can, instead of going for resolution, you can add stuff. Okay, and then you can integrate. So so you have to think at this because it's some simulation are very some physical contexts are very adapted to this. So this was the paper here. So I'm not speaking about these plots. I will speak about what is hidden in the paper. You might be interested. So 15 pages of technical appendices. So the idea is to show everything. So we detail everything, how the tree works, every algorithm, pseudocode, so you can have a look. So so you can just check it and and look at how it's done. And we went to extreme conformance with Phantom, as Timothy explained. So this plot is not the most interesting in the paper for applications, but we try to measure the only super tiny residual discrepancies between, we find, for example, in the number alpha for the viscosity. So just to make sure that it's very conform to Phantom. So it's first, it confirms that our implementation is okay, and then also it goes. You can say take synergy with Phantom. So it's very helpful to compare the simulation for both codes to debug and find. Okay, and in the paper it's only SPH, but we plan to do other stuff. So it's multi-method, multi-physics code. So I will give you a bit of. So far we have done things with the bouncing off Yona's code. The perspective is to do disks, MHD, dust, and self-gravity. So we mentioned this for the SPH. So I'm not dealing too much with this. That's we already presented. But so a lot of effort in Lyon is put on the Godunov and the adaptive mesh refinement. So Shamrock in principle is a multiple method. So the idea is that with the same code, you can change your numerical method. So, and I can see a lot of problems where it's important to know whether your result depends on the numerical method and not on your physical implementation of your equation of states, of your cooling recipe, or your whatsoever. Okay. So I think this is important. So at the moment we are implementing cell gravity in two ways: conjugated gradients and multigrid. And the idea is the target, I think, very soon is to run one stellar collapse on one GPU. Okay, so this would be a big technical improvement, and hopefully next time I will show you this, but it's the target. We have implemented Dust, and we also target to implement MHD, but really gravity is extremely important and gives challenge for the load balancing. Okay. And on the numerical side, what we are, so there is a postdoc now who is implementing multiple types. So you can make particles talk with the grid, particles talk with particles, grid talk with grids, and you can do dark matter, stars, and dust. So this is important for whatever you are doing. But the idea is to go to cosmology for the Ramses bit at least. Okay. So next priority, radiation. Because very quickly you realize that when you start to do this resolution, science at this resolution, you can just not concentrate and not do dissipation correctly. It's impossible. So I think it's a top priority. I think it's the except from very peculiar setups like compressible turbulence or this kind of stuff. But if you want to look at astrophysical system, you need gravity and really proper dissipation. So I think it's a priority target. Then we are working. There is work in progress to discuss with more HPC guys to implement multi-GPU MCMC. So if you want to like MC first, how you do this on exascale simulation, okay? But it requires some development, but it's in the pipeline. Plus also there is a HPC optimization in the load balancing. So the key test. So somebody mentioned that the setup is a bit easy for the scaling. And it's fair, it's easy, it's the easiest case. The hardest case is 1 star. 1 star, you collapse. And then the thing is that in Shamrock, the way the load balancing has been done, it has been abstracted. So we can try different models of load balancing. And the idea is to have fair comparison on this test. And then, okay, we can see if we are competitive. Okay. It's harder than the cosmological simulation where you collapse a lot. So then the load balancing is more effective. Okay. An example of what we learned by doing so is it's a bit more technical. So we implement multi-fluid drag in the Godunov part with the idea ultimately of, for example, doing some collapse of some planets. It's kind of stuff. But yeah, so set of equation on conservative way. But for the drag, you have this very simple equation So in a rescale variable, you have first order partial differential equation to invert. The question we ask ourselves is, okay, you are doing exascale simulation, so you are paying a lot. We know that some processes are very sensitive, like string stability, to the kind of like when you do a multi-spaces string stability, so you want a very accurate algorithm. So is it worth doing exascale simulation with a crappy algorithm? Well, we don't know if it's crappy, so you have to compare to something. So let's try to, so what is done in the community, for example, is implicit analytic order 1 algorithm. Let's implement exponential, and let's see what we learn from this, okay? And we did this in two codes, so it's the work done by Leodas Sewanu. And it's very, it's some tests. So what I'm showing here, it's so the test performed with two codes, so Shamrock and Diablo, which is a similar initiative done in CLA in France. I'm showing, so I'm just looking at the drag routine, the drag cancel. So I've extracted this from the idle. And I'm showing the time per cell for the drag. So the lower you are, the faster you are, okay, for different number of those spaces, okay? For the species, 8 dose species, 16 up to 32, because after, yeah, you are just killing your simulation and you don't want to do this. And by doing so what you have is that, for example, we know that how it scales. So we expect at least 2 main contributions, for example, for the computational time. It's a matrix operations, which would scale at the number of species to the cube. It's just brute force. Okay, a bit, it's not naive, but it's brute force. Then there is a cost for the communication, it scales like n, and then there are other stuff that exist. Okay. So what we were surprised because, like in one code, so in Shamrock we had like n scaling. So you are dominated by the communication, which is good because it means that the exponentiation of the matrix is just very fast. And the other code, it's n cube. And what we learned is that actually the way the code is designed is super important when you would like to implement physics. So here, what saves you is that Shamrock allows some clever use of the memory, like low memory, and then it saves you. And it was not expected. So then we just made a stop and say, okay, if you want to implement physics, but you want to keep the performance. So how you do this? And then Timothée came with an idea. He implemented extended Shamrock modules and variables. So some abstracted stuff, okay? But in a sense, is that when you use this abstracted variable or abstracted module, it handles for you the type. So it's type agnostic and it handles the memory. And just and then the idea is that you have like to do graph programming. So you think you connect operations, but automatically it handles the memory and it handles the type. So ultimately, when you want to plug alpha viscosity or whatsoever, just change your module and it handles them. It's not done, and I think it's fairly promising. Okay. And last, to finish, so the part of the project was funded by this France 2030, so Programme de Recherche Origine, which was an initiative to see if it's possible to have transition from academy to industry. Okay. So we designed the code, and with the idea, naive idea, okay, let's go to the industry. It's gonna be, yeah, we do. And then you start to discuss with industrial guys. Okay, it's not really as easy. And what we realize is that 98% of the simulation done in industry are light simulation. So the guy, what they want is that they don't want exascale. What they want is that they want multi-physics, very quick delivery, outputs for statistics of like bubbles, crazy geometries in a dishwasher, for example. And this is interesting. And it's very hard to compete with commercial code on this one. Okay, because it's all done, it's easy physics and so on. But for the 2%, for instance, the big guys, they need the resolution because they might have huge simulation that are needed for a huge reward. So, for example, I discussed with the guys from EDF, Electricity de France. Okay, and they had the problem of corrosion, and it cost them 29 billions of euros. So then it's worth like even building your own supercomputer at this stage to try to run simulation. So this is the kind of problem that is interesting for the industry. And the two things, they're like, yeah, you can ask, yeah, but why is the industry interested in the public codes? There are two reasons. First, the norms. You cannot set a norm, pass a norm to Europe with your private stuff. It doesn't make any sense. So you have to be reproducible. And second one, they like to have academic input. Otherwise, it's buy by some company, and then they sell you all the time the same stuff, the same black box. So there is no improvement in this. So in this situation, there is an interest for academic code. And so we found one guy who is interested to work with us. It's this guy, Airbus. So we have started a collaboration with them, and there is potential to collaborate. So as I told you, like this is a unique time to start with Shamrock. So if you want to try the code and try to, because it takes time to get a bit involved in the code, but I think it's a great opportunity for any of you to become the specialist of whatsoever in the code. So yeah, and we are very happy if you want to try and join. Okay, thank you.
Thanks. Very quick questions, if there are any, because we're over time.
Thanks for the talk. So I really like the idea of using different schemes in the simulation. I was wondering whether it is possible to use the different schemes in different parts of the simulation, like in a large scale, use an SPH approach while you study something in the same simulation at the same time, going like in 3 days.
Yeah, I think at the moment it's not implemented. Well, Timothy will comment on the technical aspect. I think it's a question of trade-off of risk versus reward. I think I haven't detailed because I have some ideas in mind of where you can compare the two schemes. Some interesting problem, for example, like there is problem of Hall effects in performation. The angular momentum. When you are forming some disk in some massive simulations, so, like there are some problems. Mixing the it's technically you have to ask this guy, but I think you really need to have a nice problem. Okay.
Are we anywhere close to getting one fluid and two fluids at the same time, multi-fluid simulations with a lot of fancy physics, or take months of development?
No. I think the harder stuff has been done. So the harder stuff is this what is called the layers. So the fact that you can interface a numerical object like a cell or a particle and make it abstracted, and let the two abstractions talk to each other. And so I think this was the hardest bit. Mm-hmm. I think it's nearly finished. So I think then after what is long is to test, of course. And I think Timothy, the 1.3 is.
1.3, I just need to enable the launch for the multi-grade solver.
Yes, but the multi-grade we did it with for the Godunov. So it was to do it at the same time.
I also know that at some point during a postdoc in Australia with Daniel, you tried to capture streaming instability. Do you think that Shamrock will be able to be the first SPH code to capture that thing? Because we've been talking about establishing if streaming instability could appear, but we were very far from actually capturing in SPH schemes. Do you think that Shamrock will be able to do it?
We can speak about this for a long time.
Yes or no?
In principle, yes. In theory, we can have more than 100 points per scalar and alpha close to like 10-3, 10-4. So on paper, yes.
First, so first, which streaming instability? Local box, global. Second, what do you force? Like, is it the, for example, if you are so if you are thinking of the UDIN and Johansen setup, if you don't manage it, there is something that is super fundamental.
Right, yeah, we can discuss that afterwards, maybe, if you want to do more, but let's thank Guillaume again.
Arrête le share. Stop sharing. Enfin, tu peux débrancher. Stop sharing.